Guys, hope all of us are doing fine. My name is Ernest, and this is ERNEST'S Sciences and Mathematics TV channel. Today's discussion is going to be, of course, the concept of equilibrium of a point. Now, in our previous discussion, we had looked at the concept of equilibrium in a plane, and of course, looked at some of the general way in which we are going to treat problems that are going to involve statics. And I mentioned from our introductory part the concept of statics, basically that this involves the study of forces which are in equilibrium. And of course, we are going to see that the study of the forces whose net is zero acting on an object basically is going to be entailing this specific concept of statics. Now, we're going to use this specific illustration which I've just given on my right side of the board and try to use this specific, of course, illustration to solve for this particular force given in terms of F1 and F2. Now we have been given the information of these specific angles which are going to be involved between the different types of forces. And this is going to be, of course, given between weight and F2, F1, and this specific, of course, a point of, or rather the axis of action for the F2, which is going to be the X, Y plane. And I'm going to use this specific coordinate system according to the previous procedure, which we said we are going to choose a coordinate system that is convenient. So for me, I'm going to choose the XY coordinate system, and therefore the first two which is going to be acting along the X, and this is going to be acting along the Y at an angle, and the force, of course, W is going to be acting towards gravity given in that specific direction. And therefore we have just complied with the problems which are going to be involved in this specific case for following the procedure. Now in this case, we're going to see that different letters have been used to denote the weight force, one acting on this specific direction and two, and therefore this particular angle which we are given. So revisiting our previous discussion which we had done, we had said basically that the summation of the forces which are going to be involved in this particular case along the X especially and the Y components are going to be given in terms of this, and they are going to be equivalent to zero. And this is one of the conditions which we said are going to be the case which is true for the concept of equilibrium to hold. Now in this case, we're going to look at this specific example, and as we are going to do an analysis of this, I'd said that basically we're going to consider the aspect of torque in our previous case, and this analysis basically is not going to be the case whereby we're going to consider the case of that specific torque. So having chosen our frame of reference as the XY plane given on the top right part of our previous specific illustration, therefore we can evaluate force F1 given in terms of this specific aspect of the summation of the forces which are going to be regarded with respect to the X component. And of course, we're going to see that this can be given in terms of this particular sum which can be given zero. So we can evaluate as well the forces which are going to be given in terms of this. So this is going to be the F2 particularly, which you're going to look at given in terms of the Y component. And then we're going to have F1 given in terms of the summation of Fx, of course, forces given as that one. So in this case, no, this is going to be creating a confusion for us. So particularly, we can just start with this specific reference for F1, which is going to be given as the force which is going to be given as a summation of the forces along the X. And this is going to be directed at this specific point given as such. And therefore, we can evaluate the force in the Y direction given in terms of this specific component. Now, in our last discussion, we had said that basically we can use the concept of vectors in trying to analyze these forces, whereby we're going to see that this force can be described in terms of the X and Y component. And of course, this is going to be, in terms of our Y component, we're going to give this one as F1 the sine of theta, and this is going to be given in this specific form. So in this case, we are going to see that the theta involved in this particular case is going to be the 60 degrees angle which we have been given, therefore implying that we are going to have this specific representation given in terms of F1 the sine over 60 degrees. So in this case, this is going to be the force which is going to be involved, one of the forces which are going to be involved in the F and the Y direction. And for us to find the sum of the forces which are going to be, of course, given in the y direction, we're going to include this aspect of mg, which is going to be the weight acting in the negative, of course, y direction given as that. So as we said, the forces which are going to be involved in this particular case are going to be equivalent to 0. So for us to have this particular representation, we're going to have the F1, which is going to be represented as F1 at the sine over 60 degrees, and then minus. So in this case, we're going to see that this is going to be acting opposite direction, and therefore it's going to be giving us the minus mg, which is going to be the weight of that specific, of course, mass which we have given in terms of 200 kilograms, and this is equivalent to this specific element over 0 given as that. So if we look at this one, we can just do the arrangement of this one to make F1 the subject of the formula. By having F1, the sine over 60 degrees is equivalent to mg given as that. So we can do a rearrangement for our case here. Now that we have mass and the acceleration due to gravity, we're going to use this aspect of g equivalent to 9.81. Of course, that is going to be our constant for gravitational constant, or attraction due to the force of gravity subject to this specific weight which you are given in terms of kilograms. And therefore, this is going to be given in terms of the ratio. Perhaps, okay, you can use this upper part now that we have talked about this. So we're going to have this specific representation given in terms of this function over F1 is equivalent to mg all over the sine over 60 degrees. And if we try to look at this one, then therefore this is going to be giving us the element of mass, which is 200 kilograms times 9.81 divided by the sine of that one. So if we check from our reference for the sine over 60 degrees, I hope this is going to be the figure given as that one. So the force involved in this case is going to be given in terms of newtons, which is I'm getting 2265 or 2265.6 newtons as our, of course, a force which is going to be our F1 given as that. So this is a 2265.6 newtons given as that one. So this is going to be a way in which we are going to evaluate the force which is going to be forming this specific part of known of F1. And if we try to look at the second case for the summation of forces which are going to be involved, especially in the y direction or y axis for the two coordinate system which we have chosen, we're going to see that the forces which are going to be involved in this case is a force which is given as force 2, and of course this is going to be involved in this specific y direction. And of course we're going to consider another component which I'm going to show later. So in this case we are going to have this one as a summation of forces in the x direction which are going to be equivalent to 0. So this force for F2 and another which we are going to identify in this particular case are going to be giving us a sum of 0. So we're going to have this one given in terms of this negative value over F1 at the cosine over 60. So from our previous discussion, we had identified the component of F1 along the, of course, x-axis, along the y-axis in terms of the sine function. So we are given it as F1, the sine of course, this is specific 60 degrees. But we're going to have the component of this specific force acting in the opposite direction given in terms of the cosine function. And this is going to be forming our x element of this specific resultant force given in terms of F1. So we're going to have it as a negative value of this specific illustration for the F1, the cosine over 60. And then we're going to have this one given plus the component over F2 and the cosine over 0 degrees. So in this case, so this is going to be 0 basically. So this is going to be given in terms of 0 degrees from the x-axis, which is going to be given along that specific plane. And we're going to add this one with mg, the cosine over 90 degrees. So if you try to consider from this specific case, if we are trying to find a resultant force for the concept of W and F, we're going to look at this specific aspect of the angle stretch between these two forces which we have given in terms of 90 degrees. So for us, we are going to consider this specific element of a force which we are going to give in terms of mt, and the 90 degrees stretch of an angle between the two forces for F2 and W given as such. And that's going to be forming another component of the force which we are going to come across, which is 90 degrees from the x-axis given as such. So in this case, we are going to see that the cosine of 0 is going to be giving us particularly a value of 1. And therefore, we're going to see that the cosine of 90 degrees in this particular case is going to be giving us, of course, a value of 0. So therefore, we are going to have this specific aspect of the force given in terms of F1, the cosine of 60 degrees plus F2 is equivalent to 0. And from our previous discussion, we have just basically evaluated the value for F1, which is going to be giving us a substitution for this one. And therefore, we can do a rearrangement for this particular equation and have this F1 given in terms of its particular value. Or we can as well make F2 the subject of this specific formula and have this one given in terms of F1 at the cosine of 60 degrees given as such. So in doing our substitution from the specific evaluation we did, this is 20 to 65.6, and then the cosine of 60 degrees, which we have basically, we can check this one. This is 0.5 given as that. So this is going to be giving us a force of F1 equivalent to 1132. So this 1132, and then 0.8 newtons was the amount which I'm going to be finding. So kindly check if it's going to be the case from your end. So in case you find a different, of course, value from this specific figure which I've just given, kindly notify us in the comment section, and also so that we can be able to make necessary adjustments. So this is one of the ways in which we are going to be evaluating forces which are going to be acting out of the concept of equilibrium at a point. And this is going to be involving a range of concurrent forces which I've just mentioned. And we're going to use our various, of course, a range of procedures and requirements which we are required to abide by in order to evaluate the various forces and identify the forces and the points from which they are going to be acting from. Now that is going to be forming a final bit of this specific evaluation. So kindly check our description boxes for various links of other videos. Engage us in the comment section, and also ring that notification bell for an update on different discussion we do in math and sciences. Don't forget to subscribe, and also kindly invite more members so that we can form a large community of members discussing these different topics in math and sciences. So that is it for now, guys. Bye, God bless you. Catch us in our next video.